So this recording right here is just a quick review of two of the theorems that we're using in this chapter. Now you've already learned these in 4.5 and 4.6, but I just wanted you guys to have a quick video to go back and review in case you ever had any trouble right here. So the first one is called the rational root theorem, and this is used when you have a polynomial equation that is non-factorable. It's too difficult to even get started on finding the solutions or the zeros. So right here you'll see we've got a fifth degree polynomial. There's no GCFs to take down and simplify it. There's no way to factor it by grouping or any other way. So right now there's basically no way to get started. You've got an infinite number of possibilities. What the rational root theorem does is it just gives you a starting place. Now, what we're going to do is it involves looking at your constant, which we're going to call, let's just call G for lack of a better letter, and we're going to look at the coefficient of your first term. Now remember, this has to be in standard form. So if your polynomial is not in standard form, you have to write it in standard form. So right now, your coefficient is just 1, and we're going to call that A. So what that means is if you take all the factors of G and make fractions over all the factors of A, that's going to give you a set of numbers that give you a pool that your rational zeros have to be from. So first thing to do is you know that your constant is 36. So that means all the factors of it are 1, 2, 3, 4, let's see, 6, we've got 9, we've got 12, we've got 18, and 36. So this is a number that has a lot of factors here. And luckily, the coefficient of our largest term, A, is only 1. That's the only factors in here. So what you have to do is you have to start checking each of these factors. Now remember, you also have to account for positive and negative, because -1 times -1 is still a factor. -1 times -36 gives you 36. So basically right here we have each of these numbers by themselves over 1. So that means our factors, our possible zeros, are plus or minus 1, plus or minus 2, plus or minus 3, all the way up, plus or minus 36. Now, the only reason these are just the whole numbers is because our denominator was just the factors of 1. Again, if this were 2, then we would have to put each number over 1 and then also each number over 2. So we would have 1 over 1 and then 1 over 2. 2 over 1, 2 over 2. Now, all this does is this gives us a group of numbers that our rational numbers have to be in. So the solutions, let's say a solution is 3, then that exists in this pool. So our rational solutions have to be one of these numbers. Okay, now what you do from here, you just have to taking each of these numbers and through synthetic division start plugging them in to this polynomial. See if you get a remainder of 0. If you do, then you know that number is one of your zeros. And when you do synthetic division, take the quotient, take the remaining polynomial, and now start using that to find the remaining solutions. Don't just keep going through this list right here. You've now got a smaller polynomial that may have a smaller group of numbers, or it may be factorable. Okay, so that is the rational root theorem. The other one I want to talk about is our conjugate root theorem. Now again, you learned this last section, but I just want to repeat it. What it means is that if one of our irrational roots is in the form a plus b, a plus root bi, or a plus I, so either a irrational number or a complex number. If either of our zeros or roots are in this form, then we know the conjugate has to be in this form. So if we know that a plus root b is a solution, then a minus root b also has to be. Also, if we know a plus I is a solution, then a minus I has to be a solution. Okay? And it works for both. If we know a minus root b is a solution, then a plus root b is also. Same thing for a minus I. Okay, now in this example right here, we know that 1 plus I is a 0. So try to think to yourself real quick, what else must be a 0? Take a second to think. Hopefully you came up with 1 minus I. Okay, that means that its conjugate, when we refer to conjugate, it is the same number, same terms with a different sign in between. Okay, another way to test yourself, if 2 minus root 3 is a 0 of a polynomial function, what else is a 0? Again, take 5 seconds to come up with it. And you should have come up with 2 plus root 3. So those are our two theorems that we're using in this section. You were introduced to them last section, and we're using them this section. So please, if you have any trouble, make sure you come back here and read them.